screen?
Yeah, let me go ahead and do that. You can hear me okay, right?
Yeah, no problem.
Okay. Okay, give me 1 second. Having a little bit of trouble here, but I can work around it. Okay, everyone can see, and
Yeah.
let me pull up a pointer here, and you can see the pointer.
Can you move it?
Trying to. How about now?
Yeah, still couldn't see. Yeah, still couldn't see a pointer.
Okay. Okay, well, in the interest of time, since I can't figure this out, I'll just go ahead and I will try and describe what it is that I am pointing at.
Okay, yeah, let me
Okay.
introduce. So the last speaker of our morning session is Professor Bradlyn from UIUC, and he's going to be talking about bulk properties of higher order topological insulators. You can go ahead.
Thanks, Yichen, for the introduction, and thank you to the organizers for the invitation. So this morning, I want to tell you about some work that I've been doing recently to try and look for bulk observables that can characterize higher order topological insulators. So this is work that was done in collaboration with Ben Weider, who was a postdoc at MIT and has now moved to Saclay in France, my student Quan-Sen Lin, Greg Feet, and John Palumbo. And if you want to read about things that I'm not going to have time to tell you about here or find out more, here is the archive reference for our paper where you can see everything. Okay, so I'm going to start my talk today with a brief review of topological insulators and topological crystalline insulators from the perspective of symmetry and topology, and looking at Wannier functions and Berry phases. Then I'll introduce a family of topological crystalline insulators that can have gapped surfaces. These are higher order topological insulators. A family with broken time reversal symmetry that we understand very well are so-called magnetic axion insulators, and I'll talk about those. And then try and develop some techniques based off of what we know in the magnetic case to formulate some bulk probes of non-magnetic or helical TCIs. And then I'll talk about some open questions for future research. Okay, so higher order topological insulators lie at the intersection between symmetry and topology. So topology is really the study of families of maps between different spaces. In this case, the space that we care about is the Brouillon zone that parameterizes the crystal momentum of electrons and the space of wave functions. When we introduce symmetry, which describes the crystal structure and the transformation properties of the wave functions under crystal symmetries, we can realize some new phases of matter that we couldn't otherwise. So the way that topology enters into the study of free electrons or non-interacting electron systems is by looking at how wave functions for electrons in a lattice or in a crystal depend on the crystal momentum. And so at each point in the Brouillon zone, we have some block Hamiltonian. We can look at its eigenfunctions that tell us how to assign a vector in Hilbert space, or a set of vectors in Hilbert space to each point in the Brouillon zone. And we can ask the question, can every assignment of occupied band wave functions be deformed into each other? And in many cases, the answer is no. There's different families of occupied band wave functions that can't be continuously deformed into each other without closing an energy gap. These are characterized by topological quantum numbers, such as, for instance, the simplest one being the Chern number, depicted here for a two-band system. Now, because these topological invariants are integers, they can't change continuously. So if I vary parameters in the Hamiltonian without closing an energy gap, I can't change the value of any of these invariants. So we can imagine what happens if I have some system with Chern number, any topological invariant equal to 1, and I want to, in position space, vary some parameters in the Hamiltonian such that on one side I have my topological phase, on the other side I have the vacuum, which is the simplest example of a trivial insulator. Since these topological invariants can't change continuously, something has to happen that distinguishes between my trivial and topological insulator. And in most cases, that something is the existence of a boundary gapless state. So this gives us a way to understand topological insulators by looking at the boundaries. But what's actually going on in the bulk? So one way that we can understand bulk properties of topological insulators is to ask energy eigenstates are delocalized block waves characterized by some crystal momentum. But we can try and Fourier transform these block waves and form Wannier functions, or localized orbitals, that are the analog of atomic orbitals for isolated atom. So we can start by just trying to localize the occupied electron wave functions in one direction. We'll introduce these hybrid Wannier functions that are localized in the direction x parallel, but delocalized in the perpendicular direction, so parameterized by some momentum k perpendicular. And each of these hybrid Wannier functions has a center, r sub n, that tells us where in the x parallel direction it's localized. And the center r sub n can depend on the momentum in the perpendicular direction. And so we can ask the question, can we localize these hybrid Wannier functions further in other directions? And to answer that, we can look at how the centers r sub n depend on crystal momentum. So if these centers of the hybrid Wannier functions are all roughly independent of momentum in the perpendicular direction, then I get something like, if I plot the centers as a function of momentum, something that looks like what I have on the left here, where centers wiggle around as a function of momentum, but that's about it. And so these I can Fourier transform in the perpendicular direction and get nice exponentially localized functions. But if these centers wind from one unit cell to the next as a function of perpendicular momentum, then I have a discontinuity in my hybrid Wannier functions. If I advance the crystal momentum by 2 pi, it takes me in the perpendicular direction. That should take me back to the same place. It takes me to a hybrid Wannier function that's localized 1 unit cell over. And when I go to try and Fourier transform this to get something localized in the perpendicular direction, this discontinuity tells me that I get Hauer law localized functions instead of exponential. This is depicted in the center plot here, and this gives an alternative formulation of a Z2 invariant, in this case for quantum spin Hall insulator, where I have 2 Wannier centers related by time reversal symmetry. The point is that the topological quantum numbers that we introduced to discuss families of occupied block functions, what they really tell us about is obstructions to forming Wannier functions that are localized in all directions and that obey the crystal symmetries. So this perspective has been used to great effect to characterize and classify topological crystalline insulators in all of the 230 space groups. Symmetry comes in two ways. The first thing is it can be used as a tool to help us identify different topological insulators by looking for symmetry-based indicators, simple group theory quantities that we can compute, like characters of irreducible representations that tell us whether or not a set of bands can be represented by localized Wannier functions. On the other hand, symmetry also protects new topological phases that we don't have in the absence of symmetry. And we'll see some examples of that going on. In particular, in this talk, I'm going to be focused on topological crystalline phases protected by inversion symmetry. So to get there, let's take the simplest example of a three-dimensional topological insulator. That's a 3D TI protected by time reversal symmetry.
Barry, may I ask a question?
Yes.
Can you go back to the last slide?
Yeah.
About this, the point number 2.
Mm-hmm.
And for I'm not a DFT person, but I know many DFT person, they can once they get DFT results, then they will use Wannier 90 to get the maximally localized
Right.
Wannier representation for the bands, and they match pretty well. So many of those materials are actually topologically insulated, but that fact is inconsistent with this point.
Good.
Or
Okay.
I missed anything here?
So there's a few things that could be going on. So one is for a topological non-trivial phase, the occupied bands alone don't have symmetric and exponentially localized Wannier functions. But if you consider, say, the occupied bands and then some set of the unoccupied bands that they're band inverted with, so that you consider a set of bands that as a whole is topologically trivial, even though it's divided in half, then you can use Wannier 90 to get Wannier functions that describe the occupied and the unoccupied bands just fine. So that's one thing that one possible subtlety. The other is, so the occupied bands here, the key is that they don't have Wannier functions that are both symmetric and exponentially localized. So for instance, for a 2D topological insulator, there's a very nice paper from 2011 by Soluyanov and Vanderbilt, where they look at a Kane-Millet model and try and construct Wannier functions for it. And what they find is, if you want to demand that your Wannier functions obey time reversal symmetry in position space, so that you have a Wannier function centered at site X and its time reversed partner also centered at site X, then if you try and minimize to find maximally localized Wannier functions, you get functions with power law tails. They're not exponentially localized. If you give up the requirement of local time reversal symmetry in position space, you can find exponentially localized Wannier functions. And in the Kane-Millet model, what it looks like is you have a spin up Wannier function sitting on the A sublattice of your hexagon, and a spin down Wannier function sitting on the B sublattice. And they're perfectly exponentially localized, but the Wannier description seems to break time reversal symmetry. So that's the trade-off.
I see, thank you.
Yeah. Okay, good. Thanks for the question. So let's think about 3D topological insulators. So the bulk is topologically non-trivial, which means that an interface between the bulk and the vacuum, we expect to see surface states. And in this case, a 3D TI is characterized by an odd number of surface Dirac cones. So here's STM image of what that looks like in bismuth selenide. So the only thing that we need to protect a 3D strong TI is time reversal symmetry. But if we have inversion symmetry, Fu and Kane gave us a really quick way to determine whether or not a band structure describes a 3D TI or not. What we do is we look at all the inversion symmetric momenta in the Brouillon zone. We compute the inversion eigenvalues of the occupied bands. We multiply them all together. And if the result is -1, it's a strong TI. If it's +1, it's a trivial insulator. Now, this surface Dirac cone characterization is nice, but how do we know, or how can we know from the surface what's going on in the bulk? So the issue is, if you have a single unpaired Dirac cone in a two-dimensional system, this suffers from what's known as the parity anomaly. So even though Hamiltonian for this 2D Dirac cone looks like it's time reversal symmetric, it turns out that the system is, you can't regularize the system in any way that preserves time reversal symmetry in 2 dimensions. But the surface of a 3D TI certainly has time reversal symmetry. And so the resolution of this anomaly is that it's actually the topologically non-trivial bulk that is restoring time reversal symmetry on the surface. Because the bulk of a 3D TI is described, or has electromagnetic response theory that has the Lagrangian that I've written here. The electromagnetic Lagrangian LEM for the bulk of a 3D TI is proportional to E dot B. So E dot B looks like it breaks time reversal symmetry, because B is odd under time reversal and E is even under time reversal. So the whole thing changes sign. But in quantum mechanics, it's not the Lagrangian that's important. It's, Feynman told us, it's e to the I times the integral of the Lagrangian. And the integral of E dot B up to some factors of 2 pi is always an integer. So there's 2 special values of this prefactor of E dot B where, even though the Lagrangian breaks time reversal symmetry, the action doesn't. And that's when theta equals 0 or when theta equals pi. When theta equals 0, we just have a trivial insulator. But when theta equals pi, we have a topological insulator. The bulk of the system has theta equals pi. This restores time reversal symmetry on the surface with a single unpaired Dirac cone. Now, the key point that I want to emphasize is that I can get rid of the Dirac cone on the surface of a 3D TI by only breaking symmetry on the surface. I add some magnetic impurities to the surface of a 3D TI and I can gap that Dirac cone. But the bulk has theta equals pi as long as time reversal symmetry is preserved in the bulk. And this leads to some experimental predictions where, if, as depicted in this lower picture here, if you cover the surface of a 3D TI with a ferromagnet, so you completely gap the surface, you can apply an electric field along the or a magnetic field along the axis of this 3D TI, and this axion electrodynamics Lagrangian I've written here tells you that you get a polarization quantized in units of 1/2 the electron, quantized in units of 1/2. And so even in the absence of gapless boundaries, this 3D TI still has a bulk response due to this non-trivial theta equals pi. Now, this is something I want you to keep in mind as I introduce a new class, or newish class, of topological crystalline insulators called higher order topological insulators. So these are systems where crystal symmetry stabilizes phases with more exotic boundary signatures. In fact, these higher order topological insulators are characterized by the fact that they're 3-dimensional systems whose 2-dimensional surfaces are gapless, but they feature, or gapped, sorry, but they feature gapless states on 1-dimensional hinges in highly symmetric geometries. So in panel A here, you see a sphere, and this depicts the hinge state configuration for higher order topological insulator protected by inversion symmetry. The surfaces of the sphere are gapped, but on some inversion symmetric great circle, there's a gapless hinge state. So far, we know 2 things about these higher order topological insulators. We know how to diagnose them in the bulk using symmetry indicators that generalize this Foucault formula that I showed earlier for 3DTI. And in a table here, I've shown a summary of the space groups with symmetry indicators. And we know that in highly symmetric geometries, like with global inversion symmetry, there are hinge states. Okay, the reason that this is relevant for this conference is, as we just saw in some of the previous talks, one family of materials that can realize these higher order topological insulating states are these quasi-1D bismuth halides. One particular example is the alpha phase of bismuth bromide is predicted to be a high order topological insulator, and there's even been some experimental results measuring the hinge states in the system. Now, from an experimental perspective, there are some issues with hinge states. The problem is that hinge states can be removed just by adding perturbations to the surface of the system. So if I have step edges at my surface, at each step edge, I get an additional hinge state, and this can move around the configuration of hinge states I see on a surface and even create puddles of surface states, as I've depicted on the left. And even more so, if I take a trivial system and I glue some two-dimensional topological phases onto a surface, I can get something that's trivial in the bulk, but still has hinge states because the surfaces are 2D non-trivial phases. So this raises the question of what can we measure in the bulk of a higher order topological insulator to tell us that it's really some novel phase and that we're not seeing hinge states just because the surfaces are non-trivial. So I'll focus on the simplest case, which is inversion symmetric higher order topological insulators, or Halides. And there's two different kinds of these. Both we can think of as starting from a 3DTI and either breaking time reversal symmetry by preserving inversion. This gives us a chiral phase with chiral hinge mode in inversion symmetric geometries. Or what I can do is take a 3DTI with inversion and time reversal and double it. So I double the number of occupied bands, and then I get a helical hinge state in inversion symmetric geometries. So these hinges are gappable by gluing 2D topological phases, either churn insulators in the chiral case or 2DTIs in the helical case to the surface. So what's left in the bulk?
But the way you gap the hinge state is highly non-trivial, right?
It's highly non-trivial, but it only involves perturbations on the surface. So if you look at this cube here, so here's on the bottom panel on the left, I have a cube where the up and down arrows indicate the helical hinge state. So it goes up, back, right, down, towards me, and then to the left. So to gap this, what I can do is glue a 2DTI to the front surface of this cube, the right surface of this cube, and the top surface of this cube. The intersections of all of the 2DTIs have edge states that gap out, and there's a remaining set of hinge states that gap out the hinge states of my helical Halides. So yes, it's highly non-trivial, but it is possible. Does that answer your question?
Yeah, sure,
Yeah. Okay. So the simplest case where we can really understand exactly what's left when we gap the hinge states is this chiral Halides, which are known as magnetic axion insulators. So you can think of this as taking a 3DTI and having it undergo antiferromagnetic phase transition, where time reversal spontaneously breaks, but inversion symmetry is preserved. Now, inversion symmetry, we can ask, well, when time reversal is preserved, we have this electromagnetic Lagrangian with theta equals pi, describing the bulk of the system. Now we break time reversal, so we can't use the quantization argument for theta I gave before, but we still have inversion. And E is odd under inversion, but B is even. So E dot B still changes sign under inversion, meaning that with just inversion symmetry, theta is still quantized. So this 3D magnetic axion insulator still has theta equals pi in the bulk, but it has gapped surfaces now. There's no surface Dirac cones, which means from this electromagnetic Lagrangian, the gapped surfaces of this magnetic axion insulator have half integer Hall conductivity, something that you cannot get in an isolated gap two-dimensional system. We can give a good conceptual picture of why this magnetic axion insulator has theta equals pi by going back to this Wannier function based description that I introduced earlier. So let's try and look at the hybrid Wannier functions for a magnetic axion insulator. So for the purposes of this talk, I'm going to try and localize my hybrid Wannier functions along the z direction. So I can compute the Wilson loop or the non-abelian Berry phase for occupied bands of my axion insulator to find the hybrid Wannier centers, or these R sub n for the z axis. And I've plotted here as a function of ky for some different kx, the values of e to the 2 pi I R sub n that I get for this magnetic axion insulator. And what you find is we get 3 hybrid Wannier functions. One of them has a center that's localized around the inversion center at z equals 0. And 2 of them have centers localized around the inversion center at z equals a over 2, the boundary of the unit cell. So I can think of the occupied bands of my axion insulator as being composed of block functions localized in the z equals 0 plane and block functions localized in the z equals a over 2 plane in each unit cell. And for these functions localized near z equals 0, I can compute their Chern number. And what I find is that they have Chern number minus or plus 1. And for the block functions localized near z equals a over 2, I can compute their Chern number. And they have Chern number minus 1. So what this tells me is that I can construct this magnetic axion insulator by, in an inversion symmetric way, layering Chern insulators with Chern number plus 1 at z equals 0 in each unit cell, and Chern insulators with Chern number minus 1 at z equals a over 2 at the boundary of each unit cell, which I've depicted at the bottom here. So this gives me a quasi-one-dimensional way of thinking about what a magnetic axion insulator is. And this goes under the name of layer construction. Now I can imagine a slab of 3D axion insulator with global inversion symmetry. So I just have a bunch of these unit cells. In each unit cell, I have c equals plus 1, c equals minus 1, c equals plus 1, c equals minus 1. And if I look at what I have in inversion symmetric geometry, I have half a unit cell on the top and the bottom. And each half unit cell gives me a contribution to the surface Chern number of a half. The bulk has Chern number 0. And this electromagnetic theta angle, theta equals pi, it's really telling me about the polarization of Chern number in the unit cell. If I pick my origin at 0, I have Chern number 1 at 0. So 1 times 0 plus minus 1 times a half. So I have a Chern number polarization of a half. And that is what gives me this surface half Hall conductivity. Now, this globally inversion symmetric system would have a hinge state if I made it in finite in other directions. The reason being that the Chern number on the top is plus a half relative to upward pointing normal. The Chern number on the bottom is plus a half relative to a downward pointing surface normal, relative to the upward pointing surface normal. So it's minus a half relative to the outward normal. And so the Chern number jumps by 1 at the equator. But I can add an extra Chern insulator onto the top surface so that the Chern number is constant relative to the outward pointing surface normal. That breaks the global inversion symmetry of the surface gaps out the hinge states, but it doesn't change the fact that the surface has a half integer Hall conductivity. I've just changed it from +1/2 to 1/2 -1, which is -1/2. So this implies that the surface anomalous Hall conductivity persists even when I gap the surfaces of this magnetic axion insulator. And this is really a reflection of the bulk non-trivial theta equals pi. Okay, so let's try and extend these observations to the helical Halides, the ones that preserve time reversal symmetry. Magnetic theory of topological quantum chemistry has told us that all chiral Halides have theta equals pi, so we understand those. Okay, for the helical Halide, we get this by taking a 3D strong topological insulator and doubling everything. So this has a symmetry indicator that tells us it's topologically non-trivial. And since we get it from doubling a 3D TI, it has theta equals 2 pi. But theta can be changed by 2 pi by a gauge transformation. So theta equals 2 pi is the same thing as theta equals 0. So there's no electromagnetic axion response for this helical Halide. And naively, at least the way I've introduced it, this helical Halide doesn't have obvious layer construction because a 3D TI doesn't have an obvious layer construction. But we can try and look at the hybrid Wannier functions for this helical Halide and see if we can understand things similar to what we did for the magnetic axion insulator. So again, I can try and form hybrid Wannier functions localized in the z direction. I look at my Wilson loop and I get some hybrid Wannier functions centered near z equals 0, some centered near z equals a/2. And I can look at just those functions centered near the inversion symmetric planes and look at their Chern number, or compute their Wilson loops. And what I find is that these wave functions localized near z equals 0 have a Wilson loop that winds like what I've shown on the left here. And this helical winding is what we introduced in the beginning for the hybrid Wannier centers of a 2D TI, Z2 TI. And I find the same thing for the hybrid Wannier functions centered at z equals a/2. So this gives me a layer construction, or a layer construction inspired way of thinking about a helical Halide. In each unit cell at the z equals 0 inversion symmetric plane, I have a 2D topological insulator. And the z equals 1/2 inversion symmetric plane, I also have a 2D topological insulator. And I stack these in an inversion symmetric way. But now we have a bit of a problem. In the magnetic axion insulator case, I had Chern insulator with c equals 1, and Chern insulator with c equals -1 at each unit cell. And these things are obviously different. Chern number 1 is different from Chern number -1. But 2D TIs are only described by a Z2 invariant. Each of these 2D TIs has the same Z2 invariant, one at z equals 0, one in the z equals a/2 plane. So each layer is identical. So how do I get a response? How do I learn the bulk response from a picture like this? And also, what if I try and repeat the construction I did for a finite slab for this helical Halide? I would want to say that the gapped surface of a helical Halide is in some way a half of a 2D TI, like the gapped surface of an axion insulator was half of a Chern insulator. But I don't really know what this means. So to make progress, we can use a key insight that goes back to some work by Prodan and others from about 14 years ago at this point. And we can try and divide our occupied bands in half. And we can do this using any observable we want, but one physically motivated observable that we can use is we can try and divide our occupied bands in half based on their spin. So what I mean by this is I take my occupied bands, I take this, pick a direction, let's say the Z direction, and I look at the spin operator or the matrix elements of the spin operator only in the subspace of my occupied bands. Now, if SZ is conserved for my system, then I know that it's going to have a bunch of eigenvectors that are +1 and a bunch of eigenvectors that are -1 in my occupied bands. But with spin orbit coupling, SZ is not necessarily conserved. So when I look at the spectrum of this spin operator projected into the occupied bands, I get a band that's kind of near -1 shown in blue on the right, a band that's kind of near +1 shown in orange on the right. And as long as spin orbit coupling is not so strong that these upper and lower spin bands touch, I can divide my occupied bands into the upper spin bands, the ones with eigenvalue closest to +1, and the lower spin bands, the ones with eigenvalue closest to -1. Now, I just want to point out that this spin operator projected into the occupied bands, once I make a choice of spin direction, it is a gauge invariant operator, so it's observable. It only depends on crystal momentum through the projection operator, which means that its spectrum changes smoothly as I perturb the Hamiltonian. So as I change the spin orbit coupling strength, I'm not going to all of a sudden close a gap between these upper and lower spin bands. And it's odd under time reversal symmetry, but even under inversion symmetry. So with both inversion and time reversal symmetry, like in my helical Hadi, the spectrum of the spin operator is symmetric about 0.
Hey, Barry, a reminder, 5 minutes.
Okay. Okay, so for weak spin orbit coupling, I expect the spectrum to be gap, and Prodan showed that if I look at the upper and lower spin bands for a 2D TI, the block states or the occupied states that correspond to these lower spin bands, so the ones with spin mostly pointing down, have an odd Chern number. The ones with spin pointing mostly up have the opposite signed odd Chern number. And the 2D Z2 invariant is given by the parity of this partial Chern number, the Chern number of just the mostly spin up occupied bands. I'll skip this aside for a second and just say that we can apply this procedure to 3D helical Hadis. We take our occupied bands, look at the spin operator, focus on just say the upper spin band, the mostly spin up ones, and we find that for our helical Hadi, the mostly spin up bands have the partial Chern number 1. Mostly spin down bands have partial Chern number -1. And we can do this both for the hybrid Wannier band centered near z = 0 and z = 1/2. And what we find in this case is that there's 2 ways that we can take this layer construction of a helical Hadi in terms of 2D TIs and spin resolve it. We can either have 2D TIs with partial Chern number or spin Chern number +2 at z = 0 and z = 1/2. This gives us a extensive bulk spin Chern number and extensive bulk spin Hall conductivity. Or more interestingly, we can have a case where the spin Chern number this is like a time reversal doubling of a magnetic axion insulator. The spin up electrons, or mostly spin up electrons, are like a magnetic axion insulator with theta = pi. The mostly spin down electrons are also like a magnetic axion insulator with theta = pi. The way that this manifests on gapped surfaces is that these time reversal doubled axion insulators have gapped surfaces with partial Chern numbers that are equal to 1/2. So spin Chern numbers that are odd integers, which you can't have in a gapped 2D non-interacting electron system. And we verified this numerically by computing the layer resolved Chern number for a time reversal doubled axion insulator model. What we find is that the bulk has 0 spin Chern number, so 0 topological contribution to spin Hall conductance. But the gapped surfaces in this case have a half integer contribution to their spin Hall conductivity. And this also has implications for magnetoelectric response and also the response to threading a magnetic flux, pi flux through the system. Okay, so just as an outlook, we have these 2 different ways of spin resolving helical Halides in 3D. We have these time reversal doubled axion insulators. We have 3D quantum spin Hall insulators, which have extensive bulk spin Hall conductivity. And to deform one into the other, I can deform one into the other without closing an energy gap, but I have to close a gap between the bands in the spin spectrum. And when I do that, I get some Weil points in the spin spectrum that move around and annihilate and go from one phase to the other. So this motivates refining our notion of band topology to talk about phases that are distinct, cannot be deformed into each other without closing either an energy gap or a gap in this spin spectrum. I'll just conclude by pointing out that we can apply these ideas to ab initio calculations and compute the spin spectrum and spin band topology for realistic materials. We did this for a model of beta MOTE2 zone with partial Chern number -2 from planes with partial Chern number 0. So there's several open questions for future research. One is looking for material candidates for these time reversal doubled axion insulator phases that feature these anomalous spin response properties. One thing we're working on is to develop a field theory description for the anomalous surfaces of these systems. We can extend this approach to any other observable that has 2 eigenvalues, +1 or -1, for instance, layer or valley degrees of freedom. We can look at more complicated helical topological crystalline insulators and also ask what anomalous features of these systems survive in the presence of interactions. So want to thank you all again for your attention. Sorry about the lack of pointer, and hopefully we have a couple minutes for questions.
Yeah, sure. If you have any questions, please unmute yourself.
I have one question, Barry. So have you any thought about, is there any magnetoelectric response? I mean, some concrete example as a result of your theory?
Good. So let me go back a second to this picture. So, okay, the total electromagnetic theta angle is 0 mod 2 pi. So this means that there's not going to be a robust smoking gun signature of magnetoelectric response in these systems. However, you can imagine doing the following. Say you have one of these systems very close to a spin conserving limit. So it really is something that looks like a magnetic axion insulator of spin up electrons coupled to a magnetic axion insulator of spin down electrons with some very weak spin mixing interaction or spin mixing terms in the Hamiltonian. So then what you can imagine doing is pump the surface of this system with circularly polarized light to selectively depopulate one spin species relative to the other. And if you do that, what we predict would happen is you'd create, let's say you depopulate the spin up electrons. So you have a whole pocket of spin up electrons on the surface, and this whole pocket is in a band with Chern number +1. So what you'll get in this case by selectively depopulating one spin species versus the other is then you'll get a magnetoelectric response on the surface. So you could in principle do a sort of pump probe type measurement where you depopulate one spin species and measure the Kerr rotation from the surface, and you would see magnetoelectric response that was proportional to the intensity of the pump.
I see. Thank you. So there
Yep.
a rotation issue. What do you what is this axial angle?
Right. So
It's just that theta.
Yeah, I'm calling it theta plus. What it really is you take the occupied bands, you separate them, you look at the spin spectrum, you construct the projector P plus just onto the upper spin bands, and then you compute once you have the projector, you can compute a Berry connection. So like P plus, commutator of P plus with the derivative of P plus. And then you can compute the third Chern-Simons form for this Berry connection. And that gives you this theta plus.
So the theta plus is the so-called partial axial angle.
Yeah.
Okay, great. Thank you.
Yep. Yeah, no problem. Okay, any other questions?
Yeah, so Barry, I have a question. So can you comment a little bit on the interaction generalization part? What do you expect would be changed?
Sure, okay. So there are a couple of interesting issues that come up when you want to ask what happens in the presence of interactions. So the first is this way that I've separated the bands in two is really something that is only natural when I have a non-interacting ground state, because I've really, I've found a set of single particle orbitals at each K that describe my occupied bands. And so you can ask first, how do you define these spin resolved quantities when your ground state is not necessarily a Slater determinant like this?
I see.
Time ago, but they introduced a formulation of these spin Chern numbers or partial Chern numbers using spin twisted boundary conditions. So you twist the boundary conditions on the wave functions just like you would do in the TKNN formulation of Hall conductivity, but instead of doing just a twist for all of the electron coordinates, you do a twist that depends on spin. And so you can compute the Berry curvature in the space of twisted boundary conditions to extract these Chern numbers. And so generalizing that to the three-dimensional case, I think, is something that has not been done. Aside from that, you can ask you could ask the following question, which is, I think, what we're looking at now, which is, we have these gapped surfaces with C equals 1. So tan CS equals 1, spin Chern number equals 1. And so you can ask the question, can you get sort of fractional 3D helical Halides that have gapped surfaces with other values, rational values of the spin Chern number that you couldn't necessarily get in a non-interacting three-dimensional system?
Okay, thank you.
Yeah, I have a extra question. So Barry, you are actually as a pioneer of this quantum chemistry and the topology database. So to realize this, your own theory, is there any? What are the material candidates?
Right. So the reason
just add to that, just add before you give the answer. And I had a discussion with Peter Armitage, a couple of years ago, and he said in his experiment he always prefer the materials are a kind of more insulating in some sense. That
Yes.
means the material needs to at least have, a global band gap or something like that.
Yeah. Yeah, so I agree that that is important also here. So what I can say is that at least for the simplest picture that I presented here, what we really want to look for is systems that have the symmetry indicators of a helical Hadi. So I'll put the symmetry indicators somewhere. Yeah, so no weak topological invariance and the strong Z4 index equal to 2. So that's why we chose MOTE2 as the first material that we looked at using the spin resolved formalism, because we know from a paper from the Bernevig group from a few years ago that the beta phase of MOTE2 has the symmetry indicators of a helical Hadi. So the other sorts of materials that I think I'm really excited about, and I think actually, well, that I learned about from you, are these bismuth halides. Oh, did that answer your question?
Yes, thank you.
Yeah.
Okay, any more questions? Okay, if not, let's thank Barry again, and this concludes the morning session, and let's take a break, and I hope to see you in the afternoon session.
Okay. Thanks.
Thank you.